Today I'll be showing how to control servo motors on the Raspberry Pi, and in order to do that, I'll be using this pan and tilt camera to demonstrate how. This device contains two servos which allows the camera to pan left and right and tilt up and down. As you can see, the program running right now is an auto tracker, which is able to identify a person's face or body and tracks them as they move around. I'll be showing this auto tracker program in my next video. Today's video will be an introduction explaining how to use servos in general and how to implement manual control for the pan and tilt camera using your keyboard to control its movement. Now, if you're a first-time viewer or aren't familiar with what servos are, then I recommend watching my Practical Electronics 101 playlist, specifically the episode on motors, which gives a high-level overview of some of the most common types of motors. In addition to that, I also recommend watching my Raspberry Pi playlist, and especially the most recent videos which cover PWM and brushless DC motors. Today's video will build upon what I did in those previous videos. And one last thing before we begin. If you appreciate these educational videos, then be sure to give them a thumbs up and subscribe to the channel if you haven't already. Alright, so let's begin by first going over the pan and tilt camera. The one I made works well, but I admit mine doesn't look very nice. It actually looks kinda crappy. I threw this together using mostly scrap 3D printed parts from other projects. For example, you can tell this part, which holds the bottom servo, was meant for something else which I didn't follow through with. But instead of throwing away the part, I kept it and ended up reusing it for this project. The same goes for a few other parts here. But anyway, if you have a 3D printer, then I recommend printing one of these existing designs on Thingiverse. These look a lot nicer, and there are several designs to choose from. But if you don't have a 3D printer, then you can simply purchase one. There are several different options available, so let's quickly go through a few of them. Also, I'll be putting the Amazon affiliate links for these products in the video description, so if you plan to purchase one and want to help the channel out, then be sure to use my provided links. So this first one here comes with a PCB and a pin header which plugs directly into the Pi's GPIO pins. The description also indicates it comes with a PCA 9685 chip, which isn't required to control the servos, but as I'll show later in the video, the servos won't work very well while the camera is running unless you get one of these chips. You can also purchase a dedicated board with this chip, which is what I did. But again, I'll talk more about this board later in the video. Now here's another option which has a different design but works more or less the same way. This one also contains that same chip, and personally I like this design better because it provides a sturdy base which allows it to stand on its own, without putting stress directly on the Pi's header pins. Now the last one on the list is the cheapest one and is most similar to the one I built. This one doesn't come with a PCA 9685 chip, which means you'll need to purchase the dedicated board separately. So now let's talk about the servos. All of these pan and tilt kits appear to come with two SG90 micro servos. If you search for SG90 on Amazon, you'll see a bunch of listings for it in various quantities. Each one comes with 3 different arms, and one of these is used in some of the pan and tilt kits, as you can see here. However, the problem with the SG90 is that its internal gears are made out of plastic, which means it's possible to strip them if too much force is applied to the arm. These servos are basically toys, and can easily break if you're not careful. That's why if you're 3D printing your own pan and tilt camera, then I highly suggest getting the MG90 instead, which is a drop-in replacement for the SG90, except this one has metal gears, which makes it much more durable. Even if you don't 3D print the parts and decide to purchase one of the kits instead, you should still consider replacing the servos with the MG90 to ensure better durability and longevity. Now before we move on, I also wanted to point out that you can also find larger and much more powerful servos on Amazon if you're planning to do another project. But again, these are physically larger, so they're not compatible with the pan and tilt kits for the Raspberry Pi camera. So now let's take a look at the datasheet for the MG90S. The first thing I want to point out is that these have a range of 180 degrees, which is typical for most servos. However, some models do have a larger range than this. The next thing to note is that these require between 4.8 and 6 volts to operate. Since we're using these with a Raspberry Pi, we'll be powering it directly from the Pi's 5-volt header pins. Just make sure you're using a good power supply with a high current rating. For some reason, the datasheet doesn't include the current draw, but if I Google search it, we can see each servo uses up to 250 milliamps while moving, and up to 800 if it stalls. But for this project, there shouldn't be any reason for the servos to stall if done correctly. So as long as that doesn't happen, all we need is 500 milliamps to power both servos. Now, each servo has 3 wires, a PWM pin, power, and ground. Like I've shown in previous videos, each Pi has 4 PWM pins. I'll be using pins 12 and 32 for today's example, and I'll be connecting it with these male to female jumper wires to connect the servo header to the Pi's pins. Luckily, the Pi has 2 5-volt power pins, so we can simply use one for each servo. And of course, there's plenty of ground pins available as well. Now let's go over how to control them. Each servo requires a PWM signal running at 50 Hz, and the length of each pulse needs to be between 1 and 2 milliseconds. When the signal is high for 1 millisecond, this moves the servo's arm to 0 degrees. When the signal is high for 2 seconds, that moves the arm to the other extreme, which is 180 degrees. And when the signal is high for 1.5 milliseconds, which is right in the middle of the two extremes, that moves the arm to 90 degrees. Hopefully you're seeing the pattern here. Any other angle in between 0 and 180 degrees is possible. All you need to do is provide a signal that's in between 1 and 2 milliseconds. But as you recall from my previous videos on PWM, when we change a PWM signal in Python, we need to specify the duty cycle as a percentage, not in seconds. So all we need to do is a simple conversion to determine the percent. Since we're dealing with a 50 Hz signal, this means that it has a total period of 20 milliseconds. This corresponds to a duty cycle of 100%. But we need to have a range of between 1 and 2 milliseconds. 1 millisecond is 1/20th of 20 milliseconds, which means it has a duty cycle of 5%. And 2 milliseconds is 1/10th of 20 milliseconds, which means it has a duty cycle of 10%. So in other words, all we need to do is provide a duty cycle between 5% and 10% with a 50 Hz frequency. Alright, so now let's move on to the code. This program allows you to manually control the servos using the W, S, A, and D keys on the keyboard. Holding down one of these keys will make the servo move in that direction until you release the key, or until the servo reaches its limit. The A and D keys control the panning of the camera, or in other words, the left and right motion, and the W and S keys control the tilt, or the up and down motion. Now the first several lines are actually the same as my previous example using DC motors. Here we're setting up the GPIO pins as outputs, then setting them as PWM pins with a frequency of 50 Hz. I'm setting pin 12 as the pan servo and pin 32 as the tilt servo. Next, I'm creating two variables to keep track of the current duty cycle of each servo, and I'm initializing these to 7.5% as their default position. Again, the valid range for the duty cycle is anywhere between 5 and 10%, so setting it to 7.5 will start the servos in the middle at 90 degrees. Next, I'm creating a release variable for each key. These will be set to true whenever we release a key. So now let's look at the press and release functions. Unlike my previous example with DC motors, this program contains the release function which runs whenever a key is released. So anytime the W, S, A, or D key is pressed, it'll set the respective variable to true to indicate that the key was just released. Now let's look at the press function and start with the W key. If the W key is pressed, the first thing it does is set the release W variable to false. Obviously, if the W key is being pressed, that means it's not being released, at least not yet. So we first set that to false. Next, we have a while loop that will continue to move the servo by decreasing the duty cycle as long as the key is being held down, or until the servo reaches its minimum limit. Again, the valid duty cycles are between 5 and 10, so that's why we're checking to make sure the tilt duty variable is greater than 5 here. Now, each time the loop runs, it'll decrease the duty cycle by 0.1%. Although you can increase or decrease this value if you want to change how much the servo moves at each iteration of the loop. But after experimenting with different values, I found 0.1 to be a good value here. Next, we have the change duty cycle function, which sets the servo to a new duty cycle. And finally, we have a sleep function, which pauses the program for 50 milliseconds before running the loop again. This sleep function is used to limit how fast the servo moves. If you increase the sleep time, then each loop iteration will take longer to complete, which means the servo will move slower. And if you decrease the sleep time, then the loop runs faster, which means faster servo movement. Again, this loop will continue to run until it reaches the limit of 5, or if you release the W key. When you release the W key, this function will run and set the release W key to true, which will trigger this condition to break out of the loop. Now the block for the S key is exactly the same as the W key, except now it's moving the servo in the opposite direction. It checks to make sure the duty cycle is less than 10, and if so, it will increase it by 0.1%. And likewise, the A and D keys are just like the W and S keys, except now we're dealing with the other servo to control the panning motion. Alright, so now I'll run the program, and as you can see, it seems to be working okay. I'm able to pan left and right and tilt up and down. However, if you pay close attention, then you'll notice there's some random jitters every once in a while. It's not too bad, but watch what happens when I enable the camera. So with the camera running now, you can see the servos are completely spazzing out and going crazy. This is because the way PWM was implemented in the Pi isn't very good and is susceptible to noise from other components, in this case from the camera. By the way, I'll be showing how to set up the camera and the video stream in the next video. Let's see how the PWM signal looks like under the scope. This is how it looks when the camera isn't running. It's pretty stable. And now here it is with the camera on. The signal now has severe jitter and noise. Now this really isn't a big deal for controlling brushless DC motors, where the PWM signal gets averaged out to determine the voltage that goes to the motor. But that's not the case with servos, since these contain a controller which requires a precise PWM signal. But fortunately, there is a solution, and that's the PCA 9685 board that I showed earlier. This board provides up to 16 precise PWM signals, and is controlled by the Raspberry Pi through the I2C bus. Since this is a separate board, the noise from the camera doesn't affect its PWM signals. I'll also include in the video description an Amazon link for this 2-pack, along with a link for these female-to-female header wires in order to connect the board to the Pi. Connecting it is pretty simple. These pins here are for servos and include 16 different channels for up to 16 servos or other devices. The pins are designed for the servo header, so all you need to do is plug it straight in like this. Just make sure the colors match so that the orange wire goes to the yellow pin. Now these pins here are for the Pi. First connect the SDA and SCL pins from the Pi to the respective pins on the module. These are for the I2C bus. Next, you'll need to connect ground to ground and VCC to a 5-volt power pin on the Pi. This is what powers the chip on the module. And finally, you'll need to connect the V+ pin to the other 5-volt power pin on the Pi. This is what provides power to the servos. Since we're only using 2 servos for this project, then it's fine to power this directly from the Pi, as long as you have a good power supply like I talked about earlier. However, if you're planning to run more than a couple servos, then you don't want to connect the V plus pin to the Pi. Instead, you'll want to connect a second power supply to the terminal block here. And of course, make sure you use a 5-volt supply that can provide enough current for all the servos. Now let's go back to the code and modify it for the PCA 9685 module. I'll provide the code on my website at the bottom of the GPIO guide. If you haven't seen my previous video on sensors, then you'll want to follow these steps in my guide to activate the I2C bus. Next, install the Adafruit Servo Kit Python library with this command here. I've also included the SSH keyboard library here in case you don't already have it installed. Now here's the updated code, so let's quickly go through it. The first difference is that we're now importing the new Adafruit Servo Kit library instead of the RPi GPIO library. The next line here initializes the board, and since this particular board has 16 channels, you'll need to indicate that number here in the argument. If you have a board with a different number of channels, then you'll need to put that number here instead. Next, I'm declaring 2 variables which will hold the pan and tilt angles instead of the duty cycle. Since this library was specifically designed for servos, this means we can simply provide the desired angle instead of the duty cycle. I've set the initial position for each servo to 90 degrees. Next, these commands set the angle for each servo. In the brackets, you'll need to indicate which channel you want to control. Channel 0 is on the far left, and channel 15 is on the far right. I decided to use channel 0 for the pan servo, and channel 1 for the tilt servo. Now the press function is extremely similar as before, but instead of checking for the maximum and minimum duty cycle, we're now checking for the maximum and minimum angle, which is between 0 and 180 degrees. And of course, instead of setting the duty cycle with the GPIO library, we're now using this function to set the angle. I also decreased the sleep time since we're now incrementing the servo 1 degree at a time, which is a smaller increment than before, which means slower movement. So in order to make the movement faster, the sleep time was decreased. So now I'll start the camera and test out the program. And now the servos are working perfectly smooth without any jitter or unwanted movements. Everything looks good. Now a few more things to consider is that depending on the design of your particular pan and tilt kit, its range of movement might be limited. For example, you can see when I tilt the camera up all the way, it's not able to move past this position. If I try to force it past this, then that'll make the servo stall, which isn't desirable because it'll draw a lot more power and it's possible to damage the servo, especially if you're using an SG90 which has plastic gears, like I talked about earlier. The solution is to alter this condition here with an angle that'll stop the servo before it hits its physical limit. You can do this by putting a print statement here. Now I'll run the code and slowly move the servo until it stops. You can see it stopped at 10 degrees. So just to be safe, I'll increase the angle to 15 and enter it here as the new limit condition. Now the servo will stop at 15 degrees and won't go any further than that, preventing it from stalling. And the last thing I want to point out is that depending on how the servos are orientated in your kit, you might need to reverse the direction in the code. For example, on mine, you can see this servo is orientated like this, but on this other kit, that servo is orientated in the opposite direction, which means its movement will be opposite of mine. If yours is like this one, then you'll likely need to swap these 2 lines of code, and also swap the minimum and maximum conditions like you see here. After doing this, your pan and tilt camera should move in the correct direction. Alright, so that wraps up today's video on servos. Like I said, my next video will be a follow-up on this one and we'll be going into detail on how to run an auto tracking program on the Raspberry Pi 5. If you enjoyed this video, then be sure to give it a thumbs up and subscribe to the channel if you haven't already. As always, thanks for watching, and I'll see you in the next one.